Hello, my name is Wang-Do Kim. I'm from University of Engineering and Technology, UTEC, Lima, Peru. This presentation is highlighting my key contribution and aligning with the award context. Good morning. Afternoon. Esteemed colleagues, it is an honor to present my research on measuring affordances, a concept central to understanding how organisms interact with their environment. Affordances, as defined by James J. Gibson, are not abstract physical properties, but are unique to each animal, shaped by their posture, behavior, and capabilities. My work bridges this ecological theory with biomechanics, offering a novel platform to quantify affordances in locomotion and manipulation. Traditional physics-based measurement falls short in capturing affordances because they are relational. They depend on the interaction between organism and its environment. For example, a golf club's inertia may afford a skilled golfer a fluid swing, but disrupt a novice motion. This challenge lies in developing a framework that represents this uniqueness while providing measurable insight. To address this, I turned to the theory of screws, particularly the coordinate of a cylindroid. This mathematical framework allows us to model the distribution of inertia and potential parameters, such as the ellipse of inertia and ellipse of potential across the screws. These parameters represent affordances like swing efficiency and control, uniquely perceived by each individual relative to their biomechanics. In my research, I applied this framework to analyze the symmetry and asymmetry of golf swing. Skilled golfers align their motion with harmonic screws, where inertia and potential affordance converges, resulting in efficient energy transfer and free flow motion. Novices, however, often deviate from this screw, leading to bound flow and inefficiency. This demonstrates how affordances are not universal, but tailored to each golfer's capability. To further this analysis, I integrated Turing's computational model, treating the golf swing as a state-driven process. Skilled golfers efficiently process environmental affordances, minimizing internal corrections, while novices over-rely on internal adjustment. This computational approach enhances our understanding of affordance-driven symmetry and informs artificial intelligence-driven training methodology. My key contribution is a platform that measures affordances relative to organisms, using the theory of screw and computational modeling. This framework not only advances sports biomechanics, but also has broad application in rehabilitation, robotics, and human-computer interactions. It respects the uniqueness of each individual's perception-action coupling, offering a new lens to study movement and interaction. In conclusion, my research bridges ecological theory and biomechanics, providing a measurable framework for affordance. By aligning the theory of screw with the computational model, we can better understand how organisms interact with their environment, tailored to their unique capability. Thank you for your attention, and I look forward to your question. Acknowledgement. I would like to thank the International Research Hypothesis Excellence Award for this recognition and my colleagues for their support in this research. Together, we continue to explore the fascinating interplay between organisms and their environment.